Okay, game plan for today is 11.6 and maybe some of 11.7. So let me show you this little calendar. So I've updated it. I was finished with 11.5. I put a question mark there. I wasn't sure if I could finish it last time, but I was able to finish it. The alternating series test. Quick look about something. Bear with me. Okay, so big new section is 11.6. Now 11.7 is not really a new section. It's just a combination of 11.1 to 11.6. Okay, so it's just doing some more problems, as it were. Okay, so I'm going to aim to do 11.6, some of 11.7, and then give you the quiz. Tuesday, finish 11.7 and do 11.8. So in terms of new material, we're really just doing one new material section-wise. It's 11.6. And then next time, 11.8 is also considered new. Okay. All right, so let me get started with 11.6. There's a lot of stuff in it, so let's try to jump right to it. The homework is 1 to 31 odd, 35, 37. And again, as I do the problems, my problems may not match yours, but we know the way the game works. It doesn't matter as long as you're learning your stuff. Okay. So 11.6. There's something called absolute convergence. This is on page 737. Absolute convergence. Even though it's called absolute convergence, you should think of it as absolute value convergence. You see there's absolute values there. Okay, so absolute convergence, absolute value convergence. Then we have more tests, one called the ratio test and the root test. The ratio test is a biggie. We'll be doing the ratio test the rest of the semester pretty much. The root test, not so much, but it's there. All right, so given any series, we can make up a corresponding series, summation of absolute value of A sub n, which really means if your series has positives and negatives, just make them all positive. Absolute value of A1 plus absolute value of A2 plus absolute value of A3 and so on. The terms are the absolute values of the terms of the original series. Okay, so whereas before you might have positives and negatives, okay, now just make them all positive. Okay? So of course, if your series already only had positive terms, then it doesn't matter whether you have absolute value or not. It's the same thing. All right, so definition. Again, if you want to put this on your cheat sheet, you may. Page 737. A series, notice the quote-unquote lazy notation. They don't put n equals 1 to infinity like over here, right? Or maybe 2 to infinity or 0 to infinity. It's just some series. It's called absolutely convergent if the series of absolute values, summation of absolute value of A sub n, is convergent. Okay, so absolutely convergent. Can you guess my abbreviation? AC. Okay, and by the way, the book also uses that in the back of the book. Okay, so absolute convergence, AC. Okay, so and note, if summation A sub n is a series with positive terms, then absolute value doesn't matter. It's the same thing. Okay. All right, so absolute convergence, if I take the series of absolute values of all the terms, it's convergent. So they give us some examples. Okay, summation -1 to n minus 1 over n squared. Okay, this one's alternating, we know. 1 minus 1 over 2 squared, 1 over 3 squared, minus 1 over 4 squared. Okay. They're saying this is called absolutely convergent. Because if I take the absolute value of all the terms, okay, then all the numerators are 1, right? Right now it alternates positive 1, negative 1. If you make the bars, they're all 1s. Okay. Now, this is a convergent P series, right? Where P is 2, which is greater than 1. Okay, so by definition, this series is absolutely convergent. Okay. On the other hand, example 2, the alternating harmonic series, we know it's convergent. Okay, we did that last time, right, by the alternating series test. But it's not absolutely convergent, because this time if I take the absolute value of all the terms, I get the regular harmonic series. I know the regular harmonic series is divergent. So this converges, but it's not absolutely convergent. Right? So absolute convergence, the concept is take the absolute value of all the terms, make them all positive. If that new series converges, then the original series is called absolutely convergent. Now the definition, top of 738, Notice again the lazy notation. Summation A sub n is called conditionally convergent. Now, you don't feel like writing that whole thing out. I don't feel like writing that whole thing out. We need an abbreviation, CC. Right? So for us, AC, not air conditioning, but AC is absolutely convergent. CC, not cubic centimeters or whatever, conditionally convergent for us. If the series is convergent, but not absolutely convergent. Okay? So the series I just showed you, the alternating harmonic series, right? It converges, but if I take the absolute value of all the terms, then they're all positive, it won't converge. So that's what's called conditionally convergent. Okay, and we have a theorem. We won't prove it. The book goes over the proof there. But if a series is absolutely convergent, then it's convergent. Okay. I guess it makes sense just by normal laws of language and grammar, right? Absolutely kind of modifies convergent, so it implies that. Okay, but we can't use that in mathematics. So if you want to look at the proof, the book goes over the proof. You can look at it or not. It's up to you. Okay, so the reason why we say this is that sometimes you look at a series and you say, I might have a tough time figuring out if it's convergent. Sometimes it's better to shoot for absolute convergence. Okay, because if you can shoot for absolute convergence, then you automatically have convergence. Okay, so sometimes we say absolute convergence implies convergence. Okay, or we'll say AC, and if a series is AC, then it's also C, absolute convergence and convergence. Let me show you an example of that. Okay, summation n equals 1 to infinity, cosine n over n squared. So cosine 1 over 1 squared, cosine 2 over 2 squared, cosine 3 over 3 squared. Okay, now this is not alternating. Okay, you can try it on your calculator, but if you punch out cosine 1, cosine 2, cosine 3, okay, it bounces up and down. Sometimes you have 3 positives in a row and then maybe 2 negatives in a row and then 2 positives, 3 negatives. Okay, it's not alternating, so I can't use any rule about alternating series. However, if I consider the absolute value of all the terms, then I have this, right? I already know that n is positive, so n squared is positive. Okay, I know that absolute value of cosine n is less than or equal to 1 over n squared. Okay, so I can do the comparison test. For the comparison test, you have to have positive terms. Right? Now, what do I know about summation of 1 over n squared? It's a convergent P series, so anything below it, which has positive terms, also converges by the comparison test, right? So summation of 1 over n squared is a P series with P equal to 2, greater than 1. This converges. Therefore, this series is converges. So by definition, the original series is absolutely convergent. And since it's absolutely convergent, it's also convergent. Okay, so in this particular instance, you aim for absolute convergence, and then that automatically gives convergence. Okay, so that's that. Now for a real big test. Excuse me. 739, ratio test. This is a biggie. Ratio test, you take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. The n plus first term divided by the nth term in absolute value. Okay, if you get a limit L which is less than 1, the series is absolutely convergent and by definition therefore convergent. If the ratio is bigger than 1 or infinity, the series is divergent. Okay. If the limit is 1 or the limit doesn't exist, the ratio test is inconclusive. That means it still might converge, it still might diverge. You can't tell by the ratio test. Okay. Right? Put this on your cheat sheet if you wish. Okay. So you compare the n plus first term to the nth term in absolute value. If you get something less than 1, AC, absolutely convergent, therefore convergent. If you get something bigger than 1, counting infinity, I guess infinity is bigger than 1, then the series is divergent. If you get the limit exactly 1, the ratio test is inconclusive. The test fails, we sometimes say. It still might converge, it still might diverge. On the other case where the test fails is the limit doesn't exist. Okay. The text gives you a little bit of a proof, but I'll just mention plausibility argument. When you compare the n plus first term to the nth term, it's sort of like making it a geometric series. Okay. So if the common ratio is 2, right, then that means a sub n plus 1 divided by a sub n is 2. Okay. Well, we may not have a series where it's exactly geometric, but this is quote unquote almost geometric. It's an almost geometric series. Okay. So when n approaches infinity, it's almost like, in this case, let's say you keep multiplying by 0.9. So what do you know about a geometric series where the common ratio is 0.9? It converges. How about over here? Let's suppose this thing exists and the limit comes out to be 1.1. So in the long run, it looks like a geometric series where the common ratio is 1.1. That diverges. Okay? But if you get exactly 1, then you can't tell, because that's called the ratio test. All right, so we're going to start doing some problems now involving all of these tests. Okay? There is going to be a root test. I'm going to hold off on showing it to you later. It's there, but there aren't that many problems involving the root test. Okay, I want you to know the root test, but it's definitely not as important as the ratio test. Oh, by the way, in case you're wondering, I did not make an abbreviation for ratio test. Okay, you can't say RT because that might be root test also. So sorry, this one you have to spell it out, but at least it's not that many letters, right? Ratio test, that's only 9 letters. Okay, you can write 9 letters. And root test, that's only 8 letters, right? So I will not accept RT. You have to write the whole thing out, sorry. Okay. But my other abbreviations, obviously, if I allowed it, like alternating series estimation theorem, ASET. Okay, there we go. I already made up conditional convergence, CC, too many letters. And if you look at the back of the book, it will say CC also. Or AC, absolutely convergent. A little bit too much writing. But ratio test, write the whole thing out. That's only 9 letters. Root test, that's only 8 letters. Okay, so I will not accept RT, just to let you know. Okay, so that's that. Okay, so I'm ready to start problems from 7.6. Okay, so they're asking sometimes for absolute convergence. So look at the directions there. Is it absolutely convergent or conditionally convergent, or maybe not even convergent at all? Okay. All right, and here's Melvin Hum version again. Similarly, okay, so series summation of a sub n is absolutely convergent, AC, if summation of absolute value of a sub n is convergent. And here's my real shortcut for the theorem that I showed you in the text. AC implies C. That arrow means a logical implication. Absolute convergence implies convergence. If you have absolute convergence, you automatically have convergence. Okay. And a definition, if a series is convergent, but the summation of absolute value of a sub n is divergent, then the series is called conditionally convergent, CC. It converges, but if I take the absolute value of all the terms, all of a sudden it doesn't converge. So that's called conditionally convergent. Okay, and these were the examples. I just rehashed what the book went over. Okay, so I'm just showing you the same thing. Summation -1 to the n plus 1 over n squared. Okay, if I take the summation of the absolute value of all the terms, make them all positive, that's summation of 1 over n squared. That converges. That's a convergent P series, where P is equal to 2, which is greater than 1. So therefore, summation of 1 over n squared is convergent. So the original series, which I'm calling S, is absolutely convergent. So the original is called absolutely convergent, and therefore it's also convergent. This one converges. On the other hand, the alternating harmonic series, 1 minus a half plus 1/3, okay, that converges by the alternating series test, AST. It's alternating. Terms decrease in absolute value, and terms approach 0. But if I take the absolute value of all the terms, that means you drop the -1. Just make it 1 over n, right? Again, -1 to the n or n plus 1 or n minus 1, it's either going to be -1 or 1, but if you put the bars, then it's all 1, right? Because the absolute value of 1 is 1, absolute value of -1 is 1. Now we know this diverges because that's the regular harmonic series. Okay? So by definition, the original series is conditionally convergent. Okay. All right, so I'll get set with the homework problems. Again, my numbering may not match your numbering. It doesn't matter. We're learning stuff. So if I happen to do a problem that's the same as yours, great. If not, then don't worry about it. Okay, summation n equals 1 to infinity, n over 5 to the n. Okay, we're going to do the ratio test. Okay, a lot of these are ratio tests. So I take the absolute value of a sub n plus 1 over a sub n. Okay, so how do I do that? Okay, so just like a function, for the numerator, a sub n plus 1. That means everywhere you see n, put n plus 1, theoretically in parentheses, but you can tell I don't need parentheses here. N plus 1 over 5 to the n plus 1. Divided by a sub n is just the original, n divided by 5 to the n. Okay, now you're all very good in arithmetic, otherwise you wouldn't be taking Calc 2. If I divide by a fraction, I'd rather multiply by the reciprocal. So leave this alone, n plus 1, 5 to the n plus 1, and just flip this one, 5 to the n over n. Okay. In fact, this is now the only time I'm going to do this step. This is such an easy step. You all get it. So in general, I'm just going to go straight to flipping the original. Okay. So again, dividing by the original. So here's the idea again. For the numerator, keep the same orientation. N's on top, 5 to the n is on the bottom, but replace it with n plus 1. And then multiply by the reciprocal of the original, like this. Okay, so I have n plus 1 over n. What is 5 to the n divided by 5 to the n plus 1? It's 1/5. Right? If you subtract the exponents, n minus parentheses n plus 1 would be 5 to the negative 1, or 1/5. Now, what happens as n approaches infinity? When n goes infinity, n plus 1 over n approaches 1. So we approach 1/5 as n approaches infinity. I.e., this series looks like a geometric series where you keep multiplying by 1/5 in the long run. Right. So therefore, therefore, the series is absolutely convergent by the ratio test. And if it's absolutely convergent, it's also convergent. Okay, so for the ratio test, if you get a number that's less than 1, AC, absolutely convergent, therefore convergent. If the ratio is bigger than 1, the series diverges. Okay, so that's how we do the ratio test. Okay, so let me remind you of it again. Show that to you. Ratio test, page 739. So take the ratio of the n plus first term to the nth term. If that limit is less than 1, AC, absolutely convergent. Greater than 1, including infinity, divergent. Equals 1, the ratio test is inconclusive. You can't tell. Okay. So just eyeballing some of these. Looks like a lot of these are not the same problems, but see that as me. Okay, my number 7. I'm just actually noticing that the one I did seems to be the book's number 7. But anyway, okay. Number 7, k times 2/3 of the k. Right, this one doesn't have any fractions, so I'll just go with it. So take the absolute value of a sub k plus 1 over a sub k. So just like a function, for the numerator, replace every k with k plus 1. K plus 1, 2/3 of the k plus 1. And then you divide it by the original. So there's the original. All right. So what is this? 2/3 of the k plus 1 divided by 2/3 of the k. 2/3. Right? You're supposed to subtract the exponents. So k plus 1 subtract k is 1. So 2/3 is 1. K plus 1 over k. Okay. Now, what does that approach as k approaches infinity? Well, when k approaches infinity, this approaches 1. So this approaches 2/3. I.e., it looks more and more like a geometric series where the common ratio is 2/3. That's convergent. So therefore, the series is absolutely convergent by the ratio test. And if it's absolutely convergent, therefore it's convergent. All right. Okay, my number 9. I'm not sure if I see that one anywhere, but whatever. Summation -1 to the n, 1.1 to the n divided by n to the 4th. Okay, this should be a giveaway as to what kind of a series? Alternating, right? But when I put the bars, okay, so here's the nice thing about the ratio test, also for the root test later. When you put the bars, you can drop anything that has that -1 thing. You can say -1 to the n plus 1, -1 to the n, -1 to the n minus 1. Remember, when you put the +1 or -1, that's just to make sure you're indexing starting with a positive or a negative. Okay? So when you're doing this stuff, just forget about it. Because what's -1 to the n? It's either going to be 1 or -1, right? But if you have it in bars, it's all 1. So normally just forget about that. Okay, so the first fraction, just keep the same orientation, meaning 1.1 is on top, n stuff is on the bottom, but change that to n plus 1, change that to n plus 1. 1.1 to the n plus 1 divided by n plus 1 to the 4th. Divided by a sub n means multiply by the reciprocal of the original. So just flip the original. N to the 4th over 1.1 to the n. Okay? It saves a lot of time to just go straight to that. You're all very good in arithmetic. That's why I just showed you one example, right? Say, oh, I'm dividing by a fraction. I'll just quickly multiply by the reciprocal, right? Why write all this out? Okay, that's an easy step. So that means n to the 4th over 1.1 to the n. Okay, and usually the way they combine is like this. Combine the 1.1 stuff and combine the 4th power stuff. Okay, so the 4th power stuff, I put it like this. N over n plus 1 to the 4th. And over here, what is 1.1 to the n plus 1 divided by 1.1 to the n? 1.1 to the 1st power. Okay, so now what happens as n approaches infinity? Okay, by the way, you notice this new notation. Okay, I'm saving you the trouble from keep writing limit n approaches infinity. Theory, we have to keep writing limit n approaches infinity, limit n approaches infinity. Okay, instead, we just won't put the limit n approaches infinity, do all this algebra, and then just say approaches whatever as n approaches infinity. Okay, so when n gets big, this ratio is 1, right? You put in a million. A million divided by 1,000,001 is practically 1. Raised to the 4th power is 1, and then times 1.1. So we approach 1.1 as n approaches infinity, i.e., in the long run, when n is real big, this looks like a geometric series, ignore the -1. It looks more and more like a geometric series where the common ratio is 1.1, which is bigger than 1. Therefore, that series diverges by the ratio test. Okay. All right, next one I was going to show you. Now I'm jumping back and forth, but there's a reason for it. I want to do some of these first. Okay, number 5, or again, I should say my number 5. And I'm not sure if I see that one anywhere. Oh, my number 5 is the book's number 3, I think. So it looks like Mr. Stewart just offset some of the problems in the 7th and 8th edition, but whatever. Okay, -1 to the n over 5n plus 1. Okay, I claim this converges. Okay, is it alternating? Yep. Terms decrease in absolute value, right? It'd be 1 over 1, 1 over 6, 1 over 11, 1 over 16, 1 over 21, right? They decrease in absolute value and approach 0. Therefore, the series is convergent by the alternating series test. However, take the absolute value of all the terms, which really means change this to 1. Summation 1 over 5n plus 1, 1 plus 1 6 plus 1 11 plus 1 16, and so on. Okay, that kind of looks like the harmonic series. Okay, in fact, if I were to integrate, you'd be doing some ln thing. So I'll compare it to summation 1 over n. All right, so limit as n approaches infinity of 1 over 5n plus 1 divided by 1 over n. Okay, that divided by that, multiply top and bottom by n. So limit n approaches infinity, n over 5n plus 1 That's infinity over infinity. You can do L'Hopital's rule. Limit n approaches infinity. Derivative of the top is 1. Derivative of the bottom is 5. 1/5. Okay, so by the limit comparison test, okay, remember you're allowed to have for the limit comparison test any positive quantity, just not 0, not infinity. So LCT, limit comparison test, says whatever happens to one happens to the other. So what do I know about summation 1 over n? That diverges. The reason being it's the harmonic series. I guess I didn't close it. I put a left paren, but I didn't put a right paren. Summation of 1 over n diverges. Therefore, summation of 1 over 5n plus 1 also diverges by the limit comparison test. Okay, bottom line. Okay. The original series converges, but if I take the absolute value of all the terms, which really means make this a 1, the series diverges. So by definition, this series is CC, conditionally convergent. Okay, next one I was going to show you is 13, and I think I'm noticing it does match our 13, does it not? Yeah, that one actually matches. So anyway, whatever. Okay, summation 10 to the n over n plus 1, 4 to the 2n plus 1. Oh boy. Okay, so let's try the ratio test. Absolute value of a sub n plus 1 over a sub n. Okay, so the way it works in general is the first fraction, keep the same orientation, meaning 10's on top, 4's on the bottom, n's on the bottom. But everywhere you see n, replace it with n plus 1 in parentheses. 10 to the n plus 1, n plus 1 plus 1. And this one's a little tricky. 4 to the 2 parentheses, n plus 1 plus 1. So erase that n, put parentheses. And you say, how am I going to do that over here? Technically, it's always supposed to be parentheses, but you can tell if you put parentheses here, right? Suppose I put parentheses here. 10 parentheses n plus 1. Well, that's the same as just saying, n plus 1. All right, that's going to be 10 to the n plus 1. That's n plus 2. 4 to the 2n plus 2 plus 1. So 4 to the 2n plus 3. Okay, now again, it's supposed to be divided by the original. Means times, flip it. So on the bottom is 10 to the n. On top is n plus 1, 4 to the 2n plus 1. Okay. All right. Now a little bit of algebra. N plus 1 over n plus 2. Okay, we got that. Let's compare the 10 stuff. What is that divided by that? 10 to the n plus 1 divided by 10 to the n, 10 to the 1. How about the 4 stuff? 4 to the 2n plus 1 divided by 4 to the 2n plus 3. So if you subtract 2n plus 1 minus parentheses 2n plus 3, you would have 4 to the negative 2. 4 to the negative 2 is 1/16. 10 over 16. All right, so as n approaches infinity, what happens to this expression? N plus 1 over n plus 2 approaches 1. So we approach 5/8. That is, this series in the long run, when n is real big, 1,000, 1,000,000, 1,000,000,000, 1,000,000,000,000, it looks more and more and more like a geometric series where the common ratio is 5/8. What happens for a geometric series where the common ratio is 5/8? That converges. So therefore, the series is absolutely convergent by the ratio test. That's what we're saying. Okay. Okay, so we will do some more. My 17 doesn't match, but maybe it's your 31. Okay. 17, it looks like 31. Yeah, anyway. Notice it started at 2. What's wrong with 1? ln 1, 0. Okay, it's alternating. Starting with a positive or a negative, be careful. We're starting at 2. So if you plug in 2, you get 1. So it's going to go 1, -1, 1, -1 on top. And then ln 2, ln 3, ln 4, ln 5, right? Okay, is it alternating? Yep. So if you see it's alternating, how can you tell it's alternating? The -1 stop, right? So it's alternating. Terms decrease in absolute value. Yep. Do they approach 0? Yep. Afterwards, 1 over ln 1,000, 1 over ln 1,000,000, 1 over ln 1,000,000,000. Okay, that gets really, really small. Okay, so the series is convergent by the alternating series test. Okay, but is it absolutely convergent or conditionally convergent? So now take summation of absolute value of -1 to the n over ln n. Okay, so if you take absolute value, the -1 stuff just becomes 1. Right? Summation 1 over ln n. Okay. Now, that kind of looks like a harmonic series, so I will compare it to the harmonic series. Now, here's the graph of y equals x. Here's the graph of y equals ln x. I can change it to n. So x is greater than ln x. Do you agree? Look at the graph. Likewise, n is greater than ln n. Here's y equals x. Y equals ln x. This stays above this. So if I change the letter to n is greater than ln n. Therefore, by the reciprocal rule, 1 over n is less than 1 over ln n. Right? Remember I showed you the reciprocal rule? If a is greater than b, then when you take the reciprocal, the inequality reverses. Right? Like what? 3 is less than 5. 3 is less than 5, but if you take the reciprocals, 1/3 is bigger than 1/5. Is that right? The reciprocal rule. So that means 1 over n is less than 1 over ln n. And what do I know about summation of 1 over n? Diverges because it's a harmonic series. Okay, the smaller series diverges, blows up, goes to infinity. What does it mean about this series? It also has to go to infinity. This cannot converge. How can this converge if it's bigger than something which diverges to infinity, in fact? Right? So by the comparison test, summation of 1 over ln n also diverges by CT, comparison test. All right, so getting back to where we were, the original series converges, but if I take the absolute value of all the terms, the series diverges. Therefore, by definition, the original series is conditionally convergent. Okay, you can use this abbreviation. Notice if you get used to the abbreviation, right, rather than writing the series is conditionally convergent, a lot of writing, SCT, very fast. Right. All right, now we have some problems involving factorials. So my 25, looks like you're 19. Yeah. So my 25 is your 19. N to the 100th, 100 to the n divided by n factorial. Okay. Before going on, let me just mention something quickly. N to the 100, that's already a pretty big number, right? Even if I plug in 2, 2 to the 100th is huge, right? 2 times 2 times 2, 100 times. 10 to the 100th, 1,000 is really big. 100 to the n is also pretty big, right? I mean, 100 squared is already, what, 10 to the 4th power? 100 to the 100th is huge. Okay, but how does that compare to n factorial? Okay, so let's do ratio test. A sub n plus 1 over a sub n. Okay. So again, the way it works is a sub n plus 1, keep the orientation. That's on top, that's on top, that's on the bottom, but change every occurrence of n to n plus 1 in parentheses. N plus 1 to the 100, 100 to the n plus 1, n plus 1 factorial. Yes, technically they're all parentheses, but you know, if you put parentheses here, it's the same thing. divided by a sub n. How do I divide by a sub n? I multiply by the reciprocal. So I just flip this. Times n factorial over n to the 100, 100 to the n. Right? Okay, now remember a while back, we talked about this, because I mentioned before we would get this, right? What is n factorial over n plus 1 factorial? So the strategy is, think which has more, the top or the bottom, and how many more factors does it have? N factorial, n plus 1 factorial. The bottom has more. How many more factors does it have? Exactly one more, n plus 1. Right? So there's n plus 1. Okay. N factorial means 1 times 2 times 3, dot, 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 times n. This is 1 times 2 times 3, dot, 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 times n plus 1. So everything will cancel out except there's an extra n plus 1 in the bottom. Is that right? Okay, n plus 1 to the 100th divided by n to the 100th. I can write it like that, n plus 1 over n to the 100th. And then what about these two? 100 to the n plus 1 divided by 100 to the n, 100. All right, now what happens to this as n approaches infinity? This approaches 1, right? 1 to the 100, but this goes to 0. So the series is absolutely convergent by the ratio test. Okay. All right, the problem's actually finished, but I'll dig deeper. Remember, I was trying to hype up the numerator, but the numerator is real big here, and this numerator is real big here too, right? The factorial function beats both of these. In fact, it beats both of them combined. In fact, so much so, n factorial beats these two by how much? As you go farther and farther and farther out, it looks like you're multiplying by 0. If you can imagine that. That's how much the factorial beats both of these combined. Okay? Maybe that's the reason why it was factorial. It grows real fast. Wow. Or something like that, right? The factorial. Okay. So yeah, that grows pretty fast. That grows pretty fast. N factorial beats both of them combined. So much so that in the long run, it looks like you're multiplying by nothing. Believe it or not. So that's how fast factorial grows. All right. Okay, and let's see. I think I'll go ahead and show you the root test now. I'm ready for that. There's just a couple of problems involving the root test. Okay, root test. Page 741, as you might guess, we're taking a root. How do you do the root test? You take the nth root of the absolute value of the terms. Nth root of absolute, again, there's an absolute value involved. Nth root of absolute value of a sub n equals L, which is less than 1. The series is absolutely convergent and therefore convergent. So a lot of the rules here seem to be exactly the same as for the ratio test. Okay. Less than 1, absolutely convergent. If limit n approaches infinity of the nth root of absolute value of a sub n is bigger than 1 or infinity, the series is divergent. That's exactly like the ratio test. And if you get 1, the root test is inconclusive. And also if the limit doesn't exist. If the limit doesn't exist, you can't conclude anything either. Okay. It's another instance of a quote unquote almost geometric series. Okay. But this language is exactly the same, right? Less than 1, absolutely convergent and therefore convergent. Greater than 1, divergent. Equals 1, and they don't put it, but also doesn't exist. The root test is inconclusive. Okay. Here's a very simple example. That yellow thing. Every now and then this thing turns yellow and okay, example 6. Test the convergence of this series. Okay. You might say, how do I know to do the root test? You can tell when they put something like this, it's easy to take the nth root. Right? What's the nth root of an nth power? You just drop it. So look at what you did. You took the nth root of the absolute value. Well, in this case, you don't have to worry about absolute value. Everything's positive. You're only plugging in positive for n, right? N is 1 for infinity. So what's the nth root just take off the n. And what is that ratio? It's 2/3. They did all this stuff, divide top and bottom by n. Or you can do L'Hopital's rule, 2/3. Okay, that's less than 1. Therefore, it's absolutely convergent and therefore convergent by the root test. Okay, so it's almost like this. If I ignore the exponent for a moment, 2n plus 3 divided by 3n plus 2. When n is super big, it's practically 2/3, right? You sort of just cover this up. It's 2n divided by 3n, or 2/3. Okay. Plug in a billion. 2 billion and 3, that's basically 2 billion. 3 billion and 2, that's basically 3 billion. So if you divide them, it's 2/3. It's like a geometric series, 2/3 to the n, where the common ratio is 2/3. If the common ratio is 2/3, that's a convergent geometric series. Okay. All right, so let me show you a couple of root test problems. My 21 and 23, which do not match yours, but they actually tell you the 25. Yeah, actually, my 21 is your 25, and my 29, or sorry, my 23 is your 29. Okay, so I'm doing 2 of them anyway. Good. So again, they just, looks like Mr. Stewart just renumbered. All right, now you say, how do I know to do the root test? If you have an nth power, that's a good time to do the root test, because it's very easy to take the nth root. So here's the root test. Find the limit as n approaches infinity of the nth root of the absolute value of the expression to the nth power. Okay. Yeah, this time I write limit. For the root test, I put limit. And so you didn't do that for the ratio test. Yeah, because usually the ratio test, there's so much set up, and you have to write so many other things. I didn't write the limit stuff right until the very end when I drew arrows, right? I approaches whatever as an approach to infinity. Here, it usually comes out pretty fast, so I just go straight to it. So I put the absolute value by definition, but you can tell the absolute value of this is the same thing. So I take off the n. So n squared plus 1 over 2n squared plus 1. You can do L'Hopital's rule, or divide top and bottom by n squared, right? So limit n approaches infinity. 1 plus 1 over n squared. 2 plus 1 over n squared. Okay, so when n gets big, that goes to 0. That goes to 0. The ratio is 1/2. Okay. So if you look back here, when n is super big, you forget about the plus 1, right? If I plug in a million, million squared plus 1, million squared. 2 million squared plus 1, 2 million squared. It's basically a million squared divided by 2 million squared, which is a half. In the long run, it looks like 1/2 to the n. Geometric series with a common ratio of a half that converges. So the series is absolutely convergent by the root test. Okay, so again, the concept is it's quote unquote almost geometric. Same thing for the ratio test. It's an almost geometric series. Okay, and 23 is a little bit harder. Okay, or what was it again? 29 or 29, I guess. Okay. Summation n equals 1 to infinity. 1 plus 1 over n to the n squared. Okay, so take the limit n approaches infinity of the nth root of the absolute value of the original. But again, everything here is positive, so don't worry about that. Okay, now if I raise something to the nth squared, the nth root means I can raise it to the 1 over n power. And now I have a rule that says if I have a power, another power, you can multiply the powers. So limit n approaches infinity of 1 plus 1 over n to the n. Some of you might recognize this from Calc 1. This is actually e. Okay. Now, if you don't remember that, we can do some of the tricks we did before. Like call it y. Let y be 1 plus 1 over n to the n. Ln y equals n times ln 1 plus 1 over n. And if I multiply by n, I divide by 1 over n. This kind of gets in the way there. Like that, right? Multiplying by n, divide by 1 over n. Now, limit n approaches infinity of ln y, limit n approaches infinity of this. So when n gets big, That's 0. 1 plus 0 is 1. Element of 1 is 0, so that's 0 over 0. So that means I can do L'Hopital's rule. So the derivative of the top is 1 over 1 plus 1 over n times the derivative of this, which would just be the derivative of 1 over n. And that's what I'm doing on the bottom also. So in other words, I'm writing it like this. Limit of z approaching infinity, 1 over 1 plus 1 over n times the derivative of this, which is 1 over n prime. And what was I going to do down here? I was going to take 1 over n prime. So I can cancel the 1 over n primes. And now what is this? As n approaches infinity, this becomes 0. So I have 1 over 1, which is 1. Okay, so the limit as n approaches infinity of ln y is 1 exponentially e. Okay, so the limit as n approaches infinity of y is e. E is about 2.7. Okay. That is greater than 1. Therefore, the series diverges by the root test. All right. So in other words, for this series, in the long run, it looks like a geometric series where you keep multiplying by e, 2.7. That's a divergent geometric series. So the series diverges by the root test. Okay, what time is it? 8 o'clock. Okay, I'll go a little bit longer. Okay, my 27 does not match yours, but it's a little bit harder maybe. So that means I'll do a harder one, I guess. It looks kind of weird. -1 to the n minus 1. Okay, this is almost like an odd factorial. 1 times 3 times 5, da da da, 2n minus 1. So you're not multiplying all the numbers up to something, you're only doing the odd. 1, 3, 5, 7, and so on. Okay, and then 2n minus 1 factorial. Okay. So how can I make heads or tails out of that one? Looks real weird, but it's not so bad after all when you look at it. Okay, absolute value of a sub n plus 1, a sub n. Drop this, right? It's in the bars. So this expression, you know it's either going to be 1 or -1, but when you have the bars, it's always 1. So forget about it. Okay, this part, 1 times 3, blah, 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 leave that on top. Factorial, leave in the bottom. Everywhere you see n, change it to parentheses, n plus 1. So it's going to be 1 times 3 times 5, 2 parentheses, n plus 1 minus 1. That's a dot there for multiplication. That's not a factorial. Sorry. 2 parentheses, n plus 1 minus 1. The second fraction, you're dividing by the original, which means flip this. So the factorial is on the top, the bottom is 1, 3, 5, and so on. Okay, now here's the kind of tricky part. 1, 3, 5, and so on. This comes out to be 2n plus 1. Right? 2n plus 2 minus 1. Now, how far apart are these guys? 1, 3, 5, 7. They're 2 apart, right? They're 2 apart from each other. So this is the last expression, last factor. What's just before 2n plus 1? 2n minus 1. Again, these are 2 apart, 1, 3, 5, 7. Okay. So if the last one is 2n plus 1, the factor before that is 2n plus 1, subtract 2, so 2n minus 1. And by the same logic, this is 2n plus 2 minus 1, 2n plus 1 factorial. And then leave all this alone. Okay, now, look at all this stuff. 1, 3, 5, blah, 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 2n minus 1 cancels 1, 3, 5, blah, 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 2n minus 1. So all of that cancels all of that. I still have a 2n plus 1. Okay. And now look at the factorial stuff. So we looked at the factorial stuff before, right, a long time ago. What is 2n minus 1 factorial divided by 2n plus 1 factorial? Okay, so again, we'll say, which has more factors, the top or the bottom, and how many more? The bottom has more. Or again, you might say, what does the bottom have that the top doesn't have? 2n and 2n plus 1. Okay. This, by definition, is 1 times 2 times 3 times blah, 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 2n minus 1. This is 1 times 2 times 3, blah, 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 2n minus 1 times 2n times 2n plus 1. So everything's going to cancel out except for these. And what do you notice over here? These cancel out. So the absolute value of 1 over 2n. And that approaches 0 as n approaching 0, infinity. All right. So all of that to finally say, therefore, the series is absolutely convergent by the ratio test. So that's how you deal with weird-looking stuff like that. Okay. All right, then let's see. Your 39, which is my 31. The terms of a series are defined recursively by the equation a1 is 2, a sub n plus 1 equals 5n plus 1 over 4n plus 3 a sub n. Determine whether the series converges or diverges. Okay, so here's the important thing, that in a sub n plus 1 is 5n plus 1 over 4n plus 3 a sub n. We don't really care that we're starting at 2 or whatever, because we're always talking about what happens in the long run. Okay, divide both sides by a sub n. Looks like this. It's 5n plus 1 divided by 4n plus 3. Okay. And when n goes to infinity, that approaches 5/4. Right? Just drop the 1, drop the 3, right? 5n plus 1. You know, if n is a billion, you have 5 billion and 1 divided by 4 billion and 3. It's basically 5 billion divided by 4 billion, 5/4. That's bigger than 1. So therefore, the series diverges by the ratio test. Okay, folks, that's a good time to stop, I guess. Let me check the chat. Something quickly here. All right, got that. All right, no problem there. All right, so let's break. Let's see, 8:20. Start up again about 8:20. Okay, I'll do more, and then maybe do some of section 7, and then we'll take the quiz. All right, 8:20. Okay, folks, it's 8:20. Let's start back up again. So let me go back and share the screen. Okay. Unfortunately, I'm increasing the assignment a little because I recognize that some of the problems that I stopped at originally was for the 7th edition, not the 8th. Okay, so the bad news, quote unquote, is you have to include 39, 43, and 45. The good news is that I end up doing these problems anyway, just about, I think. I just did 39, okay? And I'm going to do some of 43 and 45 right now also. Okay? So 11.6, put in 39, 43, and 45. I've already done 39. Okay, so 43 says, for which of the following series is the ratio test inconclusive? That is, it fails to give a definite answer. Okay, so that is my 35, but the problems are pretty much identical also. There's A, B, C, D. I was just going to do 2 of them, A and B. Okay, summation of 1 over n cubed. Now, we already know that this series converges. It's a convergent P series. Okay, but that's not what the question asked for. It asks, what happens if I do the ratio test? So I do the ratio test, absolute value of a sub n plus 1 over a sub n. Okay, so this one we know what to do. Change n to n plus 1. Flip. N over n plus 1 cubed. That approaches 1 as n approaches infinity, right? N over n plus 1. A million over a million and 1 is practically 1. 1 cubed is 1. So the ratio test fails. Now this still converges. We know it's a convergent P series, but we just can't use the ratio test for this. Okay. Then B says, how about summation of n over 2 to the n? Okay, so do the ratio test. Absolute value of a sub n plus 1 over a sub n. So we know the way it works. Okay, replace n with n plus 1. Keep the same orientation though. That's on top, that's on the bottom. N plus 1, 2 to the n plus 1. Divided by a sub n means times the reciprocal. So I just flip this. And this happens a lot. Combine these, combine these. So n plus 1 over n. And what do I have for the 2 stuff? 2 to the n, 2 to the n plus 1. Left with the 2 in the bottom. Okay, now when n gets big, that approaches 1. So we approach 1/2 as n approaches infinity. So the series is absolutely convergent by the ratio test. So that's fine. So this looks almost geometric. When n gets really, 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 really big, it looks like you keep multiplying by 1/2. So that converges by the ratio test. All right, then finally, my 37, which is your 45. Did I put in 45? Yeah, I just added in 45. 45. Show that summation n equals 0 to infinity, x to the n over n factorial converges for all x. B, deduce that the limit n equals infinity of x to the n over n factorial equals 0 for all x. Okay, so what does that mean? Okay, so this is my 37. Notice they index at 0. And toward the end of this chapter, okay, we're getting near the end, okay, you're going to start having n beginning at 0 more and more frequently. Okay, n equals 0 to infinity, x to the n over n factorial. They're saying this converges for all x. So they have a variable here, x. So what is x? What if x is 3 or a million or pi or e or square root of 2 over 2? We're saying it's still going to converge. Okay, so how do you prove that? Let's try the ratio test. By the way, we want to see what this looks like. It's x to the 0 over 0 factorial. 0 factorial is defined. It's defined to be 1. not 0. 0 factorial is 1 by definition. It's actually a very good definition in many instances, but for now, just take it as definition. 1 factorial is also 1. This looks like x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial and so on. Okay, this almost looks like a polynomial. In fact, it is. It's an infinite polynomial. We'll be doing a lot of these later on down the line for some of these later sections. And if you want to see what some of the terms look like, 1 plus x plus 1/2 x squared plus 1/6 x cubed. Okay, sometimes I call this an infinite polynomial. Right? See, if I stop right here, oh yeah, it's 3rd degree, 2nd degree, the next one 4th degree. Well, this is infinite degree. It's an infinite degree polynomial that never stops. Okay. Well, how does that make sense? Well, it only makes sense if you plug in x and the series converges. Otherwise, the series diverges. We'll see that later. But I'm just setting you up for future classes. For now, let's do the ratio test. A sub n plus 1 over a sub n. So change n to n plus 1. X to the n plus 1 over n plus 1 factorial. Divided by a sub n. So that means just flip this. So n factorial over x to the n. And this is the way they combine. What is the x stuff? X to the n plus 1 divided by x to the n is x on top. And then look at the factorial stuff. What is n factorial divided by n plus 1 factorial? And the easiest way to think of it is which has more factors, the top or the bottom, and how many more does it have? The bottom has 1 more, n plus 1. That's the only thing the bottom has that the top doesn't, right? This is 1 times 2 times 3 times dot, 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 n. This is 1 times 2 times 3 dot, dot, dot times n plus 1. So everything else cancels out except there will be an n plus 1 left over in the bottom. Okay, and now, regardless of what x is, x can be a super big number. The main thing is that it's fixed. It's a fixed number, but n shoots to infinity. So as n shoots to infinity, this expression approaches 0 as n approaches infinity for all x. So the series is absolutely convergent by the ratio test. So here's an example where no matter what you have for x, this series converges. Then part B says, limit n approaches infinity of x sub n over n factorial equals 0 for all x. So we had a theorem that said earlier, if a series converges, then the a sub n's approach 0. Okay, so all these terms have to approach 0. The x sub n over n factorial approaches 0. Okay. All right, folks, and I'm now done with that section. Okay, so I am finished with this. I'm going to start some of 11.7. It's really just a review section. So I'll do some of this. I'll save some for next time, and then we'll take the quiz. It's about 8:30 now, so I think we're okay time-wise. Okay. So the big thing was to make sure I covered 11.6. 11.7, I can just show you quickly what it's all about. It just says strategy for testing series. In other words, it's a review of all the stuff that we've seen before. Okay, so they give you some pointers. Okay, so it's nothing new. Okay, if you see 1 over n to the p, that's a p series. Okay, converges, p greater than 1. Diverges, p is less than or equal to 1. If you notice there's a common ratio, geometric series. Summation a r to the n minus 1 or a r to the n. Okay, that converges if absolute value of r is less than 1. That means r is between -1 and 1. Otherwise, diverges. If the series looks like a p series or geometric series, maybe you can do a comparison test. Okay. If you notice right away that the terms do not approach 0, then test for divergence. Right? What is the test for divergence? If the individual terms do not approach 0, which means they don't approach anything, or they approach a number which is non-zero, use test for divergence. if you notice that you have an alternating series, like -1 to the n, or n plus 1, or n minus 1, then try alternating series test. Okay, ratio test is real good for factorials. If you have factorials, you're almost always going to do the ratio test. Okay. And sometimes other products. If you notice it's something to the nth power, it's easy to take the nth root, then maybe do the root test. They don't give us that many problems that are like that. So root test. And finally, if you notice, if I change it to an integral, oh, I can easily integrate, then try the integral test. Although that is more complicated because you have to do the integration. Right? But still, nevertheless, you can try that. Okay, so that's what's happening. So if you look at the homework problems, test for convergence or divergence, you have to kind of look at it and say, okay, which test do I want to try? Right? Will this work? Will this work? But otherwise, there's nothing new. You just have to think of all the ones that, all the things that you've tried in the past, I guess is the way to think of it. Okay? All right, so I'll show you some, and then after a while, I'll stop when I think I've had enough. Okay. And I'm noticing a lot of the ones that I have do not match yours, so maybe I'll just forget about what I did and just do them outright again. Okay, so the first one, 11.7, and let me see if that looks like anything that we have here. And no, it doesn't. Okay, so this was used to be my number 1. All right, anyway, there are powers here, so it looks like I'm going to do the ratio test. Okay, so we're in 11.7 now. So absolute value of a sub n plus 1 over a sub n. Okay, so ratio test. Change that to n plus 1, n plus 1 squared. 2 to the n plus 1 minus 1. 2 to the n. 5 to the n plus 1. And by the way, notice I changed -5 to 5 because it's in bars. All right, once it's absolute value, you can forget about -5, just make it 5. Times the flip of this, except for the -5. 5 to the n squared, 2 to the n minus 1. Okay, look at the 2 stuff. 2 to the n, 2 to the n minus 1. If you divide, you have a 2 on top. How about the 5 stuff? That and that. You're left with a 5 on the bottom. And then n plus 1 squared over n squared, write it as n plus 1 over n squared. Okay. And what happens when n approaches infinity? That's like 1. Plug in a million. Million plus 1 divided by million is 1. Square root is 1. That approaches 2/5 as n approaches infinity. Okay? In the long run, it looks like in absolute value, you keep multiplying by 2/5. That would be a convergent geometric series. So therefore, the series is absolutely convergent, and therefore convergent, that's an and symbol, and therefore convergent by the ratio test, is what I want to show you there. Okay, 13 does match, but I notice a lot of the others don't. So yeah, so again, maybe after this one, I'll just write it out. Work them out for you. Okay, 13, 3 to the n squared over n factorial. Okay, so that again looks like a good ratio test. Okay, yeah. Okay, so a sub n plus 1 over a sub n, an absolute value. These are all positive anyway. Okay, so this one, 3 to the n plus 1, n plus 1 squared, n plus 1 factorial. Divide by a sub n means multiply by the flip. So just flip it. N factorial on top, 3 to the n squared on the bottom. Okay. And once again, look for things that are similar. 3 to the n plus 1 divided by 3 to the n. 3. And we've seen this quite a bit now. N factorial on top, n plus 1 factorial on the bottom. N plus 1 on the bottom. N plus 1 squared over n squared, you can write as n plus 1 over n squared. And there we go. Now as n gets big, this approaches 1. 1 times this limit. Well, this limit is 0 as n approaches infinity. Approaches 0 as n approaches infinity. Therefore, the series is absolutely convergent and therefore convergent by the ratio test. Okay. Yeah, emphasizing that little symbol is my way of writing and back up here. And, all right? Okay. Okay, so maybe I'll just work out some of these other ones now. I'll show you number 3. So I know a lot of the semester I had it pre-made, but I don't want to do it for now because I see too much of a mismatch. So these will obviously match because I'm using it right out of the book. And number 3, please. Summation n equals 1 infinity. Negative 1 to the n squared minus 1 over n cubed plus 1. This one should be a giveaway. That tells me that it's alternating. So I'll try the alternating series test. Are these terms going to decrease in absolute value and approach 0? That's n squared, that's n cubed. In the long run, which wins? N cubed. So yes, it's alternating. The absolute value of a sub n is decreasing, and a sub n approaches 0. So therefore, this series is convergent by the alternating series test. Okay. So when you see the -1 thing, think alternating series test almost right away. Okay. All right, so I want to show you number 1. Kind of going out of order here. Summation equals 1 infinity. N squared minus 1 n cubed plus 1. Yeah, so you should be able to look at this and say, in the long run, this behaves like what other series? So the game you want to play is, when n is super big, what can I ignore? The -1 and the +1. If n squared over n cubed, what is n squared over n cubed? 1 over n, our harmonic series. So I'm going to say compare to summation 1 over n. So I'll take the ratio of this to this. You should get 1. And that will lead us to the conclusion, whatever happens to this, happens to this. Okay, so limit n approach infinity of 1 over n divided by n squared minus 1 over n cubed plus 1. Okay, and well, let's see. How about if I divide by a fraction and multiply by the reciprocal? So limit n approach infinity, 1 over n times n cubed plus 1 over n squared minus 1. Just multiply through. Limit n approach infinity, n cubed plus 1 over n cubed minus n. And yeah, L'Hopital's rule would work. Infinity or infinity. Or yeah, you could play the trick of dividing top and bottom by n cubed. But anyway, so use L'Hopital's rule. 3n squared over 3n squared minus 1. And you can do L'Hopital's rule again. Infinity or infinity. Limit n approach infinity. 6n over 6n, which is the limit of 1 or 1. Okay, so that proves that this series behaves like the harmonic series. Okay. And what do I know about the harmonic series? It diverges. So summation 1 over n diverges because it is the harmonic series. So whatever happens to this happens to the original, which I'm just about S. So therefore, the original series also diverges by limit comparison test. It's limit comparison test for that one. Okay. Let's see. I'll do 7. N equals 2 to infinity. 1 over n radical ln n. Can you see why they don't start at 1? ln 1 is 0. Okay. Well, at first glance, you might say, why don't I compare it to 1 over n that diverges? But if I go like this, what's happening? The denominator is getting bigger. The denominator is getting bigger than this whole thing is getting smaller. I would have the bigger series diverges. So I can't say anything about that one. Okay. What's the derivative of ln x? 1 over x. So this one should be the integral test. We can integrate that. Okay. So how do we integrate? Go from 2 to infinity and just change n to x. 1 over x ln radical ln x. Okay. So look at integral from 2 to infinity of the same thing, just change n to x. 1 over x radical ln x dx, which is limit b approach infinity, integral from 2 to b. Let me write it as dx. 1 times dx is dx over x radical ln x. Okay, so u equals ln x. du is 1 over x dx. And you can pretend there's a 1 there. So x equals 2. U equals natural log of 2. X equals b. U equals natural log of b. So the integral becomes limit b approach infinity. I'm now going to integrate from ln2 to ln b. ln2 to ln b. 1 over x dx is du over radical ln x is now radical u. Okay. So limit b approach infinity. Integral from ln2 to ln b of u to the negative a half du. Square root of u on the bottom means this, right? Okay, so limit b approach infinity. Okay, integral of u to the negative a half is u to the 1/2 divided by 1/2 divided by a half means times 2 from ln2 to ln b. And let's see, how about I take outside the 2, and that becomes a square root, right? Square root. So 2 limit b approach infinity radical u from ln2 to ln b, which is 2 times the limit b approach infinity square root of ln b minus square root of ln2, which is when b gets big, ln b gets big, square root of big is big. Take away this puny number, it's big. Multiply by 2, it's big. Okay, so the integral diverges. What does that mean about the series? It diverges. Okay, so whatever the integral does, the series does. So therefore, since ID what's ID? Integral diverges. So does the series diverge. Since the integral diverges, the series diverges. Okay, these abbreviations really help, so you don't have to write INTEGRAL, DIVERGES, and so on. Right? It's a lot more convenient that way. Okay, what time is it anyway? 8:45. Okay, I'll do a few more and then I'll stop, do the quiz. Okay, so the game plan is, and this is not really a new section. So I was going to do half now, and next time I'll do a little bit more and then do 11.8. Okay, the next one I'm going to show you was 11. One over n cubed plus 1 over 3 to the n. That's an n cubed. Right. That looks like a convergent P series. This looks like a geometric series with a common ratio of 1/3. So it should converge. So the idea is to split it into two, S1 and S2. So S is S1 plus S2. And we just have to show that they both converge. So S1 is summation 1 over n cubed. So right away, that converges. The reason is because it's a P series with P equal to 3. And the key thing is that it's bigger than 1. P is 3 and it's bigger than 1. S2, summation 1 over 3 to the n. And if you're not sure about that, plug in some of the terms. Plug in it's 1/3 plus 1 over 3 squared plus 1 over 3 cubed. Okay. It's a geometric series with a common ratio of 1/3. So it converges. Reason, geometric, where r is 1/3, which means absolute value of r is less than 1. Or you can also say r is between -1 and 1. All right, so series 1, S1 converges, S2 converges, therefore S converges. So S1 converges, S2 converges, therefore S, which is S1 plus S2, also converges. This is a real number. What is the real number? I don't know. We don't care. It's a real number. This is a real number. A real number plus another real number is a real number. Okay, so that's that. Okay, then I think the only other one I want to show you this type is 17. I kind of want to show you 15 also, but we'll see how much time I have. Okay, 17 summation. It's one of these weird, strange factorials again. Whoops. 1 times 3 times 5 times 2n minus 1 over 2 times 5 times 8, 3n minus 1. Okay, so it's not really a factorial, but it's factorial-like. Right, here you're jumping every 2, here you're jumping every 3. Okay, so we'll do the ratio test. A sub n plus 1 over a sub n. So 1 times 3 times 5 times dot, dot, dot. Okay, leave space to put something in here. 2 parentheses n plus 1 minus 1. 2 times 5 times 8 dot, dot, dot. 3 times n plus 1 minus 1. Times, and then over here we just flip. Right, 2 times 5 times 8 times dot, dot, dot. 3n minus 1. 1 times 3 times 5 times dot, dot, dot. 2n minus 1. Okay, Now here's the key thing. I'm running out of space here. This thing right here, 2n plus 2 minus 1, right? 2n plus 1. One more time, it's 2n plus 2 minus 1. How about this stuff? 3n plus 3 minus 1. 3n plus 2. The key is I want to put the factor just before that. Now, these are all 2 apart, right? They're 2 apart. So what's the factor just before 2n plus 1? I subtract 2, 2n minus 1. How far apart are these guys? 2, 5, 8. They're 3 apart. Therefore, if the last one is 3n plus 2, what's the one that just comes before it? Subtract 3, 3n minus 1. That's a key thing. Okay. This is equivalent to 3n plus 2, 3n plus 3 minus 2. These are all 3 apart. So the one just before this, I subtract 3, 3n minus 1. 2 parentheses n plus 1 minus 1. That's equivalent to 2n plus 1. These are 2 apart, so the one just before this is 2n minus 1. And look at this. All of that cancels all of that. All of that cancels all of that. So the only thing you have are the stuff that I haven't read. Absolute value of 2n plus 1 over 3n plus 2. Now, what does that approach as n approaches infinity? 2/3. Approaches 2/3 as n approaches infinity. Therefore, the series is absolutely convergent by the ratio test. Okay, yeah, I wanted to do one more root test. So let me speak in one way, and this will definitely be the last one, then I'll give the quiz. Okay, and so that's a nice break. So I would have done everything on this side. And so next time I'll do this side and then go on to 11.8. Okay. So 15. Summation. K equals 1 to infinity. Doesn't matter if you index with K or N or I or whatever, same thing. 2 to the K minus 1. 3 to the K plus 1 over K raised to the K power. All right, so because I have all of these exponents of K, I'd like to take the Kth root or the root test. The problem is they're not all the same. This is K minus 1, this is K plus 1, this is K. So the trick is force it to be the way you want it. In other words, they're all with an exponent of K, and then I adjust after that. So what do I mean by that? If all of these were an exponent of K, I can take the Kth root easily. So here's the trick. Just put what you want. We're cheating, right? I can take the Kth root of that pretty easily. Now I adjust. So how can I force it to be 2 to the K minus 1? Put a 2 in the bottom, right? This right here is now 2 to the K minus 1, agreed? Okay, so again, the game I'm playing is to say, I wish they all had an exponent the same, like K. So I just do it, and then just adjust. Okay, I'm supposed to have 3 to the K plus 1. So how should I adjust this? Multiply by 3 on top. Right. Now this is 3 raised to the K plus 1, agreed? So I'll just separate the 3 and the 2 and work on these 3. So the next thing I'm going to write, I will combine all of these and just leave the 3 halves separate. In fact, you can take the 3 halves outside. You can take a constant out, right? Remember, if you multiply by a non-zero constant, that does not affect convergence or divergence. So 3/2 summation 2 times 3 over k. I'm going to write it like that. 2 to the k, 3 to the k, k to the k. I can write it like this. 2 times 3 over k raised to the k power, right? Which is 3/2 summation 2 times 3 is 6. 6 over k to the k. Now I'll do the root test. Okay, which means take the nth root of this expression. So limit n approach infinity of the nth root of, technically it's the absolute value, but in this case it doesn't matter. Okay. Oh, sorry, the kth root. Let's use all these. And kth root. So the k's just cancel out, which is limit n approach infinity. K approaches infinity. These are all k's. 6 over k. And what happens when k gets big? That approaches 0. So there we go. So summation 6 over k to the k equals 0 by the root test. So the original, where you have to multiply by an extra 3 over 2, no big deal. 3 over 2 summation of 6 over k also converges. Okay. Because multiplying by a non-zero constant doesn't affect convergence. Right? And I think we'll stop there. All right, it's almost 9 o'clock. Okay, so quickly take inventory of where we were. So I finished 11.6. I've done about half of 11.7. So next time I'll finish the rest of 11.7 and hopefully do 11.8. Okay. All right, so get your cameras, your cell phones out and get ready for the quiz. Then I'll put you in your breakout rooms as usual. If your breakout room gets too few people, then be ready for me to move you. Okay. Remember, you have to justify your answers also. Okay, so here we are. Take a picture. Determine if the series converges or diverges and state why. Okay, first one, summation. N equals 2 to infinity. What's wrong with 1? Yeah, you can't plug in 1. So 1 over radical n squared minus 1. 1 over radical n squared minus 1. 2, n equals 1 to infinity. N cubed over 100 n cubed plus 2. Oh, this is better. I have to hold it up. There we go. Maybe this picture is better. Anybody want to take a picture of this? Focus is better. N cubed over 100 n cubed plus 2. And the third one, summation of -1 to the n plus 1 over cube root of n. Okay, I'll hold this a little longer, although I can't hold it steady as much. So number 1, it's 1 over radical n squared minus 1, 2 to infinity. Number 2, n cubed over 100 n cubed plus 2. Number 3, -1 to the n plus 1 over cube root of n. Worst comes to worst, this is still being recorded. You can check the video later. Okay, so go ahead and get started. I'll set up your breakout rooms.